Dear colleagues, my name is Perminov, and today I would like to present to you a project entitled UltraBot, an autonomous mobile robot for indoor UVC disinfection. Let me start from the motivation behind the research. Since April 2020 and to this day, people have been suffering from COVID-19 disease. Despite the measures currently being taken to prevent the spread of the pandemic, the situation has not yet stabilized. Although masks, gloves, and vaccinations help prevent infection, we believe that continued disinfection of the premises will significantly reduce the risk of bacterial transmission and infection. Currently, there are some ways for disinfecting premises. The most cost-effective way is a manual cleaning of surfaces such as elevator buttons, door handles, and handrails. However, this method is very unreliable and time-consuming. The chances that the cleaner misses some of the infected areas rise as the area increases. That's why this cleaning method is poorly suited for warehouses, shopping centers, and other places. The second way to disinfect premises is to use liquid-based solutions, such as disinfect sprays. For example, employees of the Dubai Roads and Transport Authority disinfect trains using aerosols. In addition, there is an unmanned solution such as an automating disinfection robot. This robot sprays disinfectant into the disinfection area. No doubt, the liquid-based solutions are more effective than manual cleaning. However, complete surface coverage cannot be achieved in this case. Also, when it comes to indoor applications, long air ventilation is mandatory to clean chemically contaminated areas. This is why liquid-based disinfection should not be used continuously when people are present in the room. The third way to disinfect premises is to use UVC-based solutions. UVC irradiation allows to successfully and effectively kill bacteria and viruses on surfaces and in the air. Currently, a set of static UVC disinfecting towers are placed in the target area and then switched on when humans are out of the area. Also, the currently developed autonomous mobile disinfection robot of UVC Robotics company can replace a set of static towers and provide a full disinfection of the target area. However, despite all the advantages, the UVC irradiation is dangerous for human eyes and skin. So the current UVC-based solutions should not be used continuously when people are present in the room. In order to overcome these restrictions, we have developed an autonomous mobile robot for indoor UVC disinfection called UltraBot. With a speed of 0.5 km/h, the robot can disinfect 4,000 square meters in 4 hours. With its sensors such as LiDARs, RGBD cameras, and ultrasonic sensors, the robot can autonomously navigate without any human support. Collision avoidance algorithms allow to prevent collisions with static and dynamic obstacles. For disinfection, the robot uses UVC lamps of 254 nanometers, and it kills more than 90% of bacteria. There is no need to refill the robot with chemicals. Also, no air ventilation required during the and after the disinfection. The robot can work in the same space as humans without irradiating them by UVC lamps because it has 2 independent units of 4 UVC lamps per each. When the robot detects a person exposed to UVC light, it can turn off 1 unit of UVC lamps on the appropriate side, leaving the other unit on. Let's talk about the mechanical structure of the robot. The robot's chassis consists of a steel plate, aluminum profiles, and wheels. A thin steel plate is located at the very bottom of the robot and serves as its base. Aluminum profiles are attached to the plate and used to mount sensors and electronics. The chassis has 2 motor wheels, 1 idle swivel trolley wheel, which makes UltraBot a differential drive robot. The robot's body shell has a cell structure consisting of 3D printed elements. This structure allows to significantly reduce the cost of the robot's shell in comparison with analogs. The robot's disinfection module consists of 2 units, 4 UVC lamps per each. Additionally, we designed 2 reflective shields made of solid anodized aluminum. This material has one of the highest retroreflective indices for the full spectrum of ultraviolet rays. To disinfect air around the robot, we designed 12 fans located lengthwise the UVC lamps. So during the work, the robot blows air streams through the lamps, functioning alike with a quartz lamp. Well, let's talk about the robot's electrical structure. Generally, the robot has two main controllers, a high-level and a low-level controllers communicating via UART interface. The high-level controller is responsible for solving SLAM, path planning, and collision avoidance tasks, whereas the low-level controller is responsible for transferring data from ultrasonic sensors and controlling UVC lamps. All LiDARs, RGBD cameras, and motor wheels are connected to the high-level controller directly, which runs on Little Nuke. The robot's power system consists of a lithium battery with a capacity of 1,200 watt-hours. Also, it consists of 220 watt inverter and electronic control gears required for UVC lamps. As a result, the system provides approximately 4 hours of continuous disinfection. In order to make the robot fully autonomous, we have developed its high-level control system. We also considered a manual control mode for ease of transportation or emergency cases. LiDAR data and wheel odometry are used to create a digital map of the environment. Then the map and the LiDAR data is used to localize the robot and find its coordinates. Then the coordinates are used for the further map creation. The map and robot coordinates, as well as LiDAR data and data from RGBD cameras, are used to produce trajectories and wheel velocities by the navigation module. As the robot is aimed to work in known and unknown environments, we used SLAM with cartographer and IMCL localization with the static map correspondingly, and we use them as localization and mapping modules. Also, the high-level controller can send commands to the low-level controller to actually control UVC lamps and LEDs. Well, as I said earlier, the UltraBot is an autonomous mobile robot. One of the most important parameters that characterizes the stable operation of a mobile robot is the accuracy of its localization. It's well known that robot localization is highly dependent on its navigation algorithms. Even a small, quick robot turn can make it lose its true position in the environment. In order to determine the influence of robot trajectories on its localization, we conducted an experiment to choose the best disinfection trajectory type in terms of localization accuracy. Localization errors were computed for trajectories based on ground truth data obtained from the Viking tracking system presented on the slide. The system tracked markers installed on the robot with a very high accuracy. The experiment was conducted in a square room of 3 by 3 meters without inner obstacles. We investigated 3 types of robot trajectories, such as S-shaped trajectory, rolling up rectangular planar spiral trajectory where the robot moved to the room center, and unfolding rectangular planar spiral trajectory where the robot moved from the room center. We computed root mean square error and the max error for each of the trajectories. As a result, the lowest root mean square error of 2.6 centimeters and max error of 6.4 centimeters correspond to the rolling up rectangular planar spiral trajectory. It happened because at the beginning of the trajectory, the robot moved very close to such obstacles as walls, which allowed its localization system to get a high level of confidence about the robot's position. In order to validate performance of the UltraBot in terms of disinfection by UVC lamps, we have conducted an experiment on range performance of static UVC disinfection. The experiment was held at an industrial warehouse, where total bacteria count values were compared before and after the disinfection, and at different ranges from the robot. To achieve that, swab samples were taken by a specialist, and then the authorized laboratory researched the total bacteria count of samples, providing results in colony-forming units per 25 square centimeters. The UVC exposure time in the experiment was 10 minutes. And as a result, we achieved a disinfection efficiency of more than 90% at a distance of up to 2.8 meters from the robot side UVC lamps. So to summarize, we have developed a new autonomous mobile robot for UVC disinfection with 2 separate units of UVC lamps, and this robot can work in the same space as humans. we found out that the best way for the robot in terms of localization accuracy is to move along the rolling up rectangular planar spiral trajectory. In this case, localization root mean square error is 2.6 centimeters and the max error is 6.4 centimeters. And these values are the lowest in compared with other trajectories. Finally, we experimentally confirmed that more than 90% effectiveness of disinfection was achieved after 10 minutes of UVC exposure at a distance of up to 2.8 meters from the robot side UVC lamps. As a future work, we're going to determine the robot's effective disinfection zone. It's not trivial because of our UVC lamp arrangement. Also, we're going to validate the robot disinfection performance in dynamic experiments. Additionally, we're going to develop the algorithm for human detection in order to not to irradiate humans by UVC light. Also, we're going to develop path planning algorithms for the UltraBot to provide fully autonomous and effective disinfection. Thank you very much for your attention. Now I'm ready to answer your questions.